I want to clarify something about the ground symbol, which again, it seemed like most people had not seen in physics before. So remember, this is just defining where 0 volts is in a circuit. Think of it like defining sea level. What I failed to mention last time is that you might see more than one of these in a circuit. And for our purposes, that is usually just because sometimes for bigger, more complicated circuits, it can get kind of cumbersome and annoying to draw lots of lines all the way back to a single ground symbol. Okay, so for a single battery-operated circuit, 9 times out of 10, if not more than that, ground is just going to be defined at the negative terminal of the battery. Okay, just kind of by convention. It is equivalent to draw that circuit like this, with 2 different grounds, where it is implied that all of the grounds are connected. Okay? Unless there's more complex situations that I don't think we'll deal with in this class, where you might have separate grounds or something, but there is kind of a implied connection between those 2 grounds that is just not drawn there. And again, it doesn't really matter here, but if you imagine, we'll see this when we look at the circuit schematic for the Arduino later in the semester. It's huge. It fills this entire page, and there's a dozen ground symbols all over the place just because they didn't want to have to draw all the lines back to one corner or something. So if you see that, again, that just means both of those points are tied to ground, which we're defining as 0 volts. Okay, so don't let multiple grounds scare you. The other kind of convention thing that I'm going to start using today is many times for a circuit with a single battery or voltage source, we don't always bother drawing the battery. So you might just see something like V in with a line going to the circuit, and then the resistor to ground, where again, it is implied in that scenario that that is some positive voltage reference to ground. Okay, we just don't bother drawing every time. Or again, it might be the little circle symbol we saw last time, so that's the same as either saying there's battery with V in or some voltage source. I also tend to be lazy about subscripts, like I might write Vs for source voltage, V in for input voltage, V bat for battery voltage. It doesn't really matter what the subscript is, right? The point is it's the input or input signal, power, whatever you want to call it. So, and for the sake of just not kind of cluttering up the diagram, sometimes we skip drawing that. You might also see another line going over here that says, say, V out. Okay, now that line is not actually connected to anything else, that's just telling you where we're measuring that voltage. So it's kind of the same as writing, say, V in and just drawing a dot there and saying V out. Those all mean the same thing, they're just different ways of drawing the same thing. Okay, again, depending on what prerequisites people took or how they did it in physics, I don't know exactly what you're used to, so I'm going to make sure you don't get confused and look at that like, wait, does that mean something different? Okay, so any questions on that stuff, like multiple grounds, voltage in and out? Good? Okay. Then, again, if you're not logged into Poll Everywhere yet, please make sure you're logged in, because I'm going to draw something here. So the question's kind of going to be on the screen, but the multiple choice answers will be in Poll Everywhere. So we are going to take the circuit that we had a rather contentious debate about at the end of last lecture, change it a little bit, but we are going to close the switch this time, and then ask a similar question. So I have this circuit, and this is what we had last time, where it was R, and a 12-volt battery with the switch open. 2 changes this time. I'm going to close the switch, so ignore the open switch. So this switch is closed, and that resistor is now 3R instead of R. Okay, and I want to know, again, what is the voltage difference between points 1 and 2. So I'm going to activate that poll. This is one where you might actually need to do a little bit of math as opposed to just kind of quickly looking at it. I'm also going to redraw this kind of using the convention I have above. That is equivalent to asking, so if I have a 12-volt input, here's R, here's 3R, and if I say call that V out or whatever, where again point 1 is there and point 2 is connected to the negative terminal of the battery, so I'm defining that as ground. These are equivalent. So another important distinction I should make, remember Voltage is always measured between 2 points, just like elevation. If you ask about the elevation of a city, it's implied that you mean relative to sea level. So if I ask you, what is the voltage at V out, which is just a point, right? I didn't tell you what the second point is, then you assume I mean relative to ground. So V out is referenced relative to ground. That is different than asking, for example, if I call this resistor R1, what is the voltage drop across R1? Okay, then I am talking about the voltage drop between these 2 points, which is not relative to ground. So whenever you see, whether it's on homework, a lab, a prelim, whatever, a question asking about voltage, make sure you read it carefully and understand what it's asking you about the voltage across or relative to. Again, using the elevation analogy, this is like asking, well, what's the elevation difference between Ithaca and Syracuse, or whatever, right? 2 different points, one of which is not sea level. Anyway, so the poll everywhere should be live. You see we have about 50 answers, so and this is still, I'm going to be sorting out some poll everywhere logistics later today, and maybe next week we'll start actually doing this for correctness, but for now it's still just participation, so don't worry if you're wrong, but feel free to kind of talk to people around you if you're not even kind of sure how to go about figuring this out. I will give it another couple minutes because we're at like 80-ish responses, and I think there's a little more than 100 people here. Okay, so again, switch is closed, pardon the scribble, switch is no longer open, and this resistor is now 3R. What is V out, or what is the difference between, voltage difference between points 1 and 2? What are the questions? Yeah, sorry, we were not, the question is not asking about this red line, that was just kind of an aside about defining voltage. We were asking for either V out or voltage difference between points 1 and 2. Okay, I just said all of that without turning it. Okay, if I'm ever talking and forgot to turn my mic back on, let me know. Okay, we're at 112 responses. I'll give it like another minute. Okay, call it 30 seconds, 15 seconds, because I think the responses are leveling off, or maybe a couple. Saw the number go back down, so maybe somebody changed their mind. 5, 4, 3. Again, if you're not sure at this point, just guess so you get the participation credit. 2, 1, deactivate. Okay, let me check the responses here. Okay, the majority, I'm not hooked up to the projector right now, so the majority of you got that right. The correct answer is 9 volts. Okay, so don't worry if you didn't get it. We are going to kind of go through the derivation for how you would figure this out, which is then going to lead into the rest of kind of today and the next couple lectures talking about resistor network analysis, which again you should have seen in physics, but if you have a circuit that just consists of resistors and batteries, how do you figure out what's the voltage over this resistor, what's the current through this resistor, what is the power dissipated by this resistor? And I always want to try and motivate things by, okay, why should you care as a mechanical engineer and not, you're not going to go get a job where somebody's just going to hand you resistors and say, solve for the current through R2, right? You care because of batteries, right? And electric vehicles. I mean, if you want to go work for Tesla, right? There is an example problem in homework 2, inspired by the FSA project team, or I don't know if I have that, one of the electric vehicle project teams, right? Batteries, which we'll talk about later today, have internal resistance, wires have resistance, so it's not necessarily the little resistors you'll use on a breadboard in lab, but real physical things have resistance. Things that have resistance get hot. Think of it like the electrical analog of friction, right? So if you have, there's a lot of different scenarios where as a mechanical engineer, you're going to need to know, okay, how hot is this going to get? So the power dissipated by the resistor is important. So kind of if you're bored of analyzing resistor circuits, kind of try to think of that as the backdrop. If you ever hear the phrase resistive load, that is talking about a load that, again, is not literally one of the little resistors you use in the lab, but something that behaves resistively as opposed to capacitively or inductively, which we'll talk about in the next few weeks. So for example, a motor is an inductive load. If you've ever noticed, like when you turn your washer or dryer on, the lights flicker a bit. We'll talk about that later, as opposed to something like a space heater that is a purely resistive load and just acting like a resistor and converting that electricity into heat. So you can kind of remember that as the backdrop as we're slogging through all the resistor stuff here. Okay, so now everybody's favorite part of lecture, where the lecturer just stands here and does a bunch of algebra. But again, I want to make sure it's clear where that 9 volts came from for people who didn't get this answer. Okay, so more generically, as opposed to doing this specifically with these numbers, if we have a circuit that is called a voltage divider, probably guess from the name, it's called a voltage divider because it divides a voltage. It takes some input voltage Vin. We have resistors R1 and R2. So it can be any value. It doesn't have to be some specific ratio like what I had there. And we have some output voltage V out. Okay, so I have an input voltage and I want to divide or lower that voltage. I can do it by choosing two appropriate resistor values. Okay, so that equation, which I'm not just going to write down, I want to go through the derivation here just real quick, comes from, you're going to remember Ohm's law. So these two resistors are in series. They're going to have some current through them. That current is the same because they're in series. I can combine them into an equivalent resistor. R EQ equals R1 plus R2, because again, the resistors are in series, so their resistance adds. And I know that, again, the current through this imaginary equivalent resistor has to be the same as the current through these two individual separate resistors. So Ohm's law applies there, right? So Vin equals I times R1 plus R2. Ohm's law also applies over here to both resistors individually, right? So I can look at Ohm's law just for resistor R2, where that resistor only has V out over it, right? So V out equals I R2. Again, I know that the I's in these two, try to use a different color here, circuits are equal, so I can rearrange both of those equations to solve for I, set them equal to each other, and then I get an equation that just gives me V out as a function of Vin and the resistor values. Okay, so if I rearrange this one first, I equals Vin over R1 plus R2. Rearrange this one, I get I equals V out over R2. Okay, set those equal to each other. Vin over R1 plus R2 equals V out over R2. I would like to get an equation that just gives me V out as a function of everything else. Okay, so I multiply both sides by R2. V out equals R2 over R1 plus R2 times Vn. Great. You never have to do that derivation again in your life. Okay, if you know that a circuit is a voltage divider, or you are asked to design a voltage divider, okay, you know that that is the equation, so just like write that down, draw a big box around it, voltage divider equation. And again, one of the kind of learning outcomes or motivations for this course is not just to be able to analyze a circuit that is handed to you, but to kind of have a library of simple circuits that do simple things and know which one does what. So if you are, say, given a homework problem or an exam problem that says, design a circuit to, just like we did there, to convert a 12-volt source to a 9-volt voltage, right? Without using the words voltage divider, you can go, oh, I can use a voltage divider to do that. And I remember the schematic and I remember the equation, okay? And again, thinking of the design aspect, you will see this on homework 2. And in real life, you're probably not going to be handed a circuit and asked to solve for a voltage, but you might need to design a circuit. So again, if I just told you, okay, I have 12 volts and we need 9 volts, design a voltage divider to do that. You only have one equation, but you have two unknowns, right? You don't know, you know your desired V out, you know your Vn, but you don't know R1 or R2, so it's an under-constrained engineering problem. But you might have other constraints like power dissipation, right? So remember, we didn't really talk about power here at all, but there's the equation for power dissipated by a resistor, which you can write in 3 different ways: IV, I squared R, or V squared over R. The tiny little resistors in your kit are only 1/4 watt. Okay? After that, they start catching on fire. So, for example, if I told you just to design a 50-50 voltage divider, right, convert 12 volts to 6 volts, you could look at that and go, oh, I can just use 2 1-ohm resistors. Mathematically correct, physically, no. Okay, that would way exceed the, you would get 1 ohm is really small, right? So from Ohm's law, you're going to get a ton of current. I squared R, that means you're going to dissipate way more than 1/4 watt of power per those 2 resistors, and poof, okay, it's going to burn out. So that is, again, literally going to, I'm pretty sure this is on homework 2, a kind of general rule of thumb here is that you're going to want to start with resistors kind of in the 1 to 10 kilo ohm range as opposed to the 1 to 10 ohm range. Because again, that way the current flow is going to be much smaller and you're not going to burn out the resistors. So that definitely, I think, happens in the past where people just do the math and pick a very small resistor value that makes the math work. But then without thinking about the power consideration, it burns things out. So I don't think homework 2 has that warning printed on it, so make a note of that now. It just tells you to design the voltage divider. It doesn't include the warning about picking really small values or kind of starting with that kilo ohm range. And again, practical examples of when this could be useful. Talking about the Arduino later in the semester. The Arduino has input pins that can read a voltage, but it can only handle up to 5 volts. After that, you risk damaging the Arduino. There are other Arduino models and other microcontrollers that only operate at 3.3 volts. Right? So maybe at some point you need 2 of those devices to talk to each other, or you have a sensor or something else that outputs something higher than 5 volts. You can use a voltage divider to safely step down the voltage so you can hook it up to the Arduino without blowing up your Arduino pin. Okay, so this isn't just kind of math for the sake of math. It's a very simple but useful circuit that you can make with just 2 resistors. Okay. Voltage divider questions. Yes?
If like VE is like a battery, what would it be out be?
And so the question was, if V in is like a battery, what would V out be? It doesn't matter what V in physically comes from, this equation still applies. Okay, so it can be a battery, it can be, if you go into the lab, there's the big benchtop power supplies. It could be a digital signal from an Arduino pin that outputs 5 volts. This equation always applies regardless of what the physical source of the voltage is. Again, we'll talk about batteries a little more today because I think we have time. Okay. Okay, we are going to switch gears a bit and talk about measurements. So we talked on, I think, Friday, we physically hooked up a multimeter to measure voltage and current. Now we're going to talk about the difference between an ideal voltmeter, which is probably how you treated things in physics and how a voltmeter works in real life. So, and again, in lab, you're going to have, in your kits, you have a single device with different settings for voltage and current, right? So here, when I say voltmeter, I mean a multimeter in the voltage setting. So, an ideal voltmeter. I'm not going to bother doing this as a poll everywhere. I'm just kind of going to write it down and circle the answer. Should the internal resistance of an ideal voltmeter be 0 or infinity? Okay, think about it for a second, and then we're just going to do a quick show of hands. Should the internal resistance of an ideal voltmeter be 0 or infinity? Raise your hand for 0. Raise your hand for infinity. Okay, some more enthusiasm for infinity. That is correct. And also, I realized the TA scanned the lecture notes in black and white from Monday, so I'm going to ask and see if he can do them in color this time, so like the color pens show up. So sorry about that, but I think Monday's notes should still be legible. So using our voltage divider example again, say I have a circuit like this with 2 resistors, and I want to measure the voltage just over this one. So this is going to be my symbol for an ideal voltmeter. If I don't I don't want hooking up measurement equipment to change what's happening in the circuit. Right? Ideally, this circuit is going to have some current I through, so call it I1 through resistor 1, I2 through resistor 2, which in this case those are equal. In order for those to be equal, I need the current through the multimeter to be 0, right? So it's not siphoning off any current, because if it does, then it changes the voltage over the second resistor, right? It's if I2 and I3 split, now the current through this resistor is different and the voltage over it can be different. So in the ideal case, you want that to have infinite internal resistance. In reality, so here's ideal. The practical or reality or whatever you want to call it case, it has some very, very large but not actually infinite resistance. So if I draw the circuit again, in reality, when I hook up my multimeter, that's my ideal multimeter, it kind of has a very, very large resistance, which we'll call RM, in parallel. This is how you model it, right? So if I draw a red box around that whole thing, this is my practical multimeter, where I model it as an ideal multimeter, which has, or ideal voltmeter, which has infinite resistance in parallel with a very, very large measurement resistance that does siphon off some non-zero amount of current, right? So in reality, I have I1 through resistor R1, I2 here, and I3 over here. It's really, really small, but it's not zero. So the act of hooking up your multimeter can actually very slightly change the voltage over what you're measuring. Is that error big enough that it matters for practical purposes as far as we're concerned in this class? Not really, but you should know that this is a thing. Okay, let me check in again. If you look, I haven't looked at we have different multimeters than we did in the kits the last time I looked. A lot of times if you look on the data sheet for a multimeter, you might see the phrase input impedance. We'll talk about impedance and the difference between impedance and resistance a little later in the semester, but it's usually something like 1 to 10 mega ohms. And so and we talked about kilo ohms a second ago with the voltage divider. Mega ohms is really, really big, so really, really high resistance. And so generally for higher quality measurement equipment, the higher the better, so you're affecting what you're measuring less. That reminds me, actually, sorry, before the next thing. So any questions on kind of the ideal versus practical multimeter scenario? Okay. Kind of an aside about units then, because we haven't, we've been talking about units, but haven't really talked about practical values and what you should expect to see in this class. So for voltage, we are usually talking about, at the end of the class, you're going to build a battery-powered robot, right, that is powered by 4 AA batteries. Those are 1.5 volts each. You connect 4 of them in series, you get 6 volts. Right? You're also going to have a 9-volt battery, which powers the Arduino separately. So when it comes to physical voltages you're measuring in a lab, we're usually talking about the order of kind of 1 to 10 volts here. If you get a lab measurement, if you take a measurement in lab, and so it's in millivolts or kilovolts, you're probably off by a factor of 10 or 1,000 somehow with your multimeter setting, or you messed up a calculation or something. If we talk about electricity from a wall outlet in the US, that's 120 volts. If you've ever looked at like a bigger dryer outlet or an electric car charger, they can be 240 volts or higher. That much voltage can usually kill you, so we're not messing with it in an undergraduate lab. We're sticking with safer, lower voltages kind of on a lab bench and battery-powered stuff. That's for voltage. For current, we measure in amps. We are usually dealing with milliamps, not amps. So an amp is a lot. Okay, an amp is, when you hear something in multiple amps, you're talking about larger motors, so something like a washer and dryer, kind of like larger appliances. For the little Arduino stuff we're going to be doing, something like an LED is maybe 20 milliamps. The smaller motors in your kit, maybe a few hundreds of milliamps, but I think the stall current, so if you grab onto a motor and stop it such that it can't spin, again, we'll talk about mechanical and electrical analogies. Think of that kind of like pushing against something as hard as you can that can't move, right? might get up over an amp. But so again, if you're doing measurements in lab and you are getting microamps or hundreds of amps or something, you're probably reading your multimeter wrong or made a calculation error. And then resistance, we've kind of has a bigger range, I guess, going from just the little jumper wires in your breadboard kit. They are almost negligible as far as we're concerned, kind of in the milliohm range. For current limiting resistors for LEDs, which we talked about 1 or 2 lectures ago, right? They're kind of in the hundreds of ohms range. And then we talked about kind of the 1 to 10K resistor range for voltage dividers. And then kind of a 1M to 10M range for input impedance for a multimeter. And pardon my terrible handwriting here, but so point being, there's a much bigger range of resistor values, so you don't necessarily need to have alarm bells go off with, like, depending on the application, there are kind of ranges of resistor values that make sense. But again, it's good to kind of have these ranges in mind in terms of what you should physically expect to see in the lab in this course. Okay? Any questions on that stuff? Yes?
I actually have a question on, can you explain the right diagram for practical?
Yes, so this diagram, so the question is, can I explain the diagram on the right for practical? This diagram on the left, I'm using the V symbol to represent an ideal multimeter which has infinite internal resistance and no current flows through it, right? This diagram on the right, the red box is around a model of a practical or real multimeter, which does have a very, very large resistance in parallel with this V still represents the ideal multimeter. So if I kind of magnify that here, and look at current coming in, the current flows through this, in the model flows through this resistor, there's still no current through the ideal multimeter part. So if you hook up a real multimeter with 2 probes, it's going to have some resistance that flows through it. But this is a mathematical model. Think of the physical device as the part encompassed by this red box that still only has 2 connections to the external circuit. The part inside the red box is just a mathematical model of it. Does that make sense?
I'm just a little confused why we're drawing this second resistor if the V has infinite resistance.
So you're confused about why I'm drawing RM if V has infinite resistance?
Yes.
Because they're in parallel, right? So current can flow through RM. Does that make sense? Right, so if, I still want to draw the V because I guess I could just not draw the V, but you know, that's just kind of the icon we use to show that we're measuring voltage. If I didn't draw RM there, then that's equivalent to this diagram where I just have a ideal multimeter, which is going to have 0 current through it.
So does the V just signify that we're just like measuring?
Yes, that's just the symbol we use for measuring voltage. Okay? Again, think of the red bounding box as the actual, like you still only have, when you go do that in the lab, you still just have you're holding a multimeter in hand with 2 wires that you connect to your circuit, right? There's not some physical device with 4 internal wires like that. Okay, and then this might make a little more sense. We're going to do the ammeter case next. So any other questions about the voltmeter part? Okay. So next up, we're going to do ideal ammeter. And most of you got the kind of poll right, so I'll just skip the hand showing this time. An ideal ammeter should have 0 internal resistance. Okay? So if we were going to again take this voltage divider circuit and say I want to hook up an ammeter to measure the current through this circuit, and we talked about this with the, I actually didn't get to this in lecture last time, but it was on the concept test and it's in the slides. Since this is all in series, I could put this ammeter anywhere here, right? The current would be the same through the entire circuit. Ideally, so that A is our ammeter symbol. We use the V for a voltmeter symbol. Excuse me. So when we hook this up, we treat the ammeter like it has 0 resistance, so there's no voltage drop across it, right? It's like it's just a wire. We don't want it to affect the circuit at all. So R equals 0. And again, when I do that, I'm not adding any additional resistance in series, so I'm not affecting the current through the circuit at all. So there's ideal. And then in reality, we model that like, I'll draw a little red box around it in a second. A very small, but not actually zero resistance RM in series with the ammeter, right? So now I have, by hooking the ammeter up, I'm adding a small resistance in series, which is actually going to decrease the current a little bit. And usually with the cheap multimeters and the student kits, as opposed to the really like expensive professional ones, you can actually kind of see how this resistance changes a bit with the different dial settings. I mean, I don't know if this is true for the newer ones in the kits, but the meters have a manually ranging dial to measure current at different levels, and you would change the dial and then see the current reading jump. Because kind of due to the internal physics of how the multimeter measures current, that resistance was actually a little different on each dial setting. So if you ever experience that in lab, like, hey, I changed the setting, why did the current change to? This is why. Okay? In reality, that resistance is small but not zero. Small but not zero. Okay. Questions on the ideal or practical ammeter situation? Yes?
For both voltmeter and ammeter, is it if it's connected to the for voltmeter, it's connected between the resistor, one of the starting point, and it ends at the right before the ground symbol.
Correct.
So it's measuring the voltage drop between the R2, right?
Correct. So the question was, what is the voltmeter measuring in this circuit? It is measuring the voltage drop over R2 there, but this is true regardless of where you hook the multimeter up. Okay, so if I wanted to hook that up over R1, that doesn't change what's in the red box there. Okay? Okay, other questions on either voltmeter or ammeter? And again, this isn't just for the sake of doing the math, this is so you understand when you physically go use a multimeter in lab or on homework what's going on. Okay, let me check what I have next. All right, let's wake everybody up a little bit with another poll everywhere. I might need to zoom for this. I guess I'm going to need to zoom quite a bit. Okay, so in case you can't see the text, focus on this part up here. So this says 19.5 volts and 2.31 amps. That's a little grainier than I would hoped it would be, but I think that's kind of the best I'm going to do here. The output is 19.5 volts and 2.31 amps. So what does this thing actually do? Look at the pole everywhere. I don't know if you all have cell phone chargers, laptop chargers. I don't know if you've ever looked at the text on these things. What does this thing physically do if it's rated for an output of 19.5 volts and 2.31 amps? And does it, the way the question's formatted on my screen here is kind of weird, but does that mean it always provides that much, both voltage and current? Does it mean it always provides a constant for one of those while the other depends on the load? Or does it mean that that's just the maximum and it will provide up to that value for both depending on the load? Okay, I think that's how I have the four answers written out, and I want to get a understanding of if people understand how DC power supplies work. The other part I'm not talking about here is these adapters are taking AC or alternating current from the wall. Right? So if you hooked an oscilloscope up to a wall outlet, which I do not want you to do, you would see a sine wave, okay, and then this converts it to a constant voltage, which then charges your phone or your laptop or whatever. So that's what all these, when you see these little bricks with chargers, that's what the electronics in here are doing, and we'll talk about that more later in the semester. Okay, we got 81 responses. So talk about it for another minute or two. We got up to around 120 last time. Okay, we're hovering around 20 again, so give it 10 seconds if you're thinking of changing your vote. 5, 4, 3, 2, 1. I'm going to deactivate and check the responses here. Maybe this time I will actually. Okay, this one I am going to hook up to the projector and show the results. Go. So 1 second as I get my mouse to cooperate. Okay, correct answer was C. It provides a constant 19.5 volts and up to 2.31 amps depending on the load. But clearly only about half of you got that right, so a lot of you probably haven't seen this before. So, switching back to the document camera. So here's what this means. Again, this does not mean that it can somehow force both that voltage and the current into a load. Again, think of Ohm's law, right? If you have a resistor and you hook it up to a battery, the battery can't force both the voltage and the current. Okay, the current is, if the battery, chemically, again, we're not getting into the physics or chemistry of how batteries work, but a battery acts like a voltage source. Okay, it provides a fixed voltage. The current that is then drawn from the battery depends on the resistor value. Okay, same thing for these adapter bricks. They act like a voltage source where they do their best to provide this constant voltage and can provide up to that current. Okay, but it's not like a hose that somehow forces a certain amount of current through no matter what the load is. So sometimes people will get this question about Arduinos a lot, where an Arduino can handle an input of, say, a 7 to 12 volt range, but you might have a power supply that's rated for 5 amps. And go, oh, is that too many amps? Is that going to blow up my Arduino? The answer is no, it's fine. The voltage is right. The Arduino will draw as much current as it needs. Okay? And we are now going to switch back over to a piece of paper to kind of talk about the mathematical model for this. So, oh, I zoomed way in. Hold on. Okay. So, if we look at, just kind of like how we looked at the mathematical circuit diagram model for voltmeters and ammeters for measurement, we're going to do the same thing for sources quickly, because I think I have less than 10 minutes left because that clock is slow. Okay. So if we don't get to current sources today, we'll do that on Friday because I want to spend time on voltage sources. So for an ideal voltage source, again, we might draw that as a battery like this. We might draw it using this little circle icon with a label like VS. Both mean the same thing, just a voltage source. For a source, we have something like an IV, something called an IV diagram. You guys, minor pet peeve of mine, if I can hear you talking up here, you're being way too loud. Okay, please don't be disruptive to the people near you. Okay, an IV diagram, so if we have a graph of current versus voltage for the supply, an ideal source can provide a constant voltage regardless of the current. Right, so this is just a straight vertical line, so it can mathematically provide infinite current. In reality, we know that's not true, right? You cannot get infinite power out of a AA battery. Okay, in reality, if you take a AA battery and just short circuit the terminals, right? Ohm's law, V equals IR. If voltage is some fixed number and R goes to 0, then so R goes to 0, then I is going to go to infinity. Okay? In reality, that doesn't make sense, right? So how do we do a practical mathematical model of this? we do that kind of like we did with the multimeter and ammeter by putting a small series resistance in series with the source. So if this is my voltage source, Vs, I now have a series resistance Rs in series with that. And if I measure the output voltage, now remember the kind of not trick question, but question about the open switch last time, right? If there's no load hooked up, if I hook a multimeter up to a battery and measure the voltage, there's no current flowing, almost no current flowing. Okay, remember with a practical multimeter, technically now I have some very, very large resistance, so there's some tiny amount of current flowing. But if a tiny amount of current is flowing, then there's almost no voltage drop across this resistor, right? So you're measuring pretty much the full voltage of the battery. But if I hook up a load, say a load resistor RL there, what do I have now? What did we do at the beginning of the lecture? What circuit is that? I hear whispers. Somebody say it louder. Two resistors in series. Voltage divider, right? So the V out in this circuit is determined by my voltage divider equation, where I have now my load resistance over my internal or source resistance plus the load resistance times Vs, or the open circuit voltage of the battery. So I should have written that down. You have the open circuit voltage of the battery when there is no load connected. Okay? So this is important for figuring out, hey, why aren't my batteries working? You hook up a multimeter to a battery that is not currently connected to a load. It's a AA battery, and you go, hey, the voltage is 1.5 volts, it's fine, why isn't my robot going? Then you hook up a load. As batteries age and deplete, that internal resistance goes up, and the voltage, when you're connected to a load, is lower, right? Because now there's current flowing, and there's a voltage drop over that resistor. Okay, so let me check. Before I switch, I'll come back to this in a second, but I wanted to quickly show if I can find it, because I left all my notes all over the place. This is something you can look up for a battery, right? If you're ever trying to size, I'll bring this one back in a second. I want to make sure I have time to show this thing I printed. If you're ever trying to figure out, okay, well, what size battery do I need and how long is it going to last, right? These graphs are taken from the datasheet for a Duracell AA battery. Okay, you can look up 4 different loads, so 5 milliamps, 10 milliamps, all the way up to a whole amp. What does the discharge curve look like, and how does the actual voltage of the battery change over time? Okay, so the other thing to mention here is that a dead battery is not literally 0 volts. Okay, if you have devices powered by AA batteries at home, you'll see that many times they will actually stop working kind of in like a little over the 1 volt range, because there's whatever the minimum voltage and ability to deliver current by the battery eventually kind of can't meet what the device needs. So again, relevant later in the semester with robots and the battery packs, just because the voltage isn't literally 0 doesn't mean the batteries are still going to work. Just because you hook it up with no load and measure 1.5 volts doesn't mean the batteries are still good. Okay, you can actually use the multimeter to measure the voltage while the motors are running, and you'll see even with brand new batteries, you'll see that voltage sag a bit. So there is some non-zero internal resistance even to brand new batteries. And again, we're not getting into I think on either in Canvas or the homework assignment, if you really want to know the details and the physics, there's a technical bulletin from Energizer that explains battery internal resistance. So there's both the kind of physical resistivity of the metal materials and everything, and then there's also a bunch of chemistry stuff going on that I won't even pretend to understand. So that's all in there and kind of explains, again, what battery internal resistance is and how it changes as the battery ages. So let me go back to, and this sheet will be part of the scan notes, so don't worry about copying that down. Okay, so here we have the open circuit voltage, where again we're measuring the voltage where there's no load connected. Here we have the voltage, you might get the phrase under load. Okay, so what is the actual output voltage of the battery? Where again, I kind of forgot to draw a little bounding box here. The stuff inside that red box is my mathematical model of a real battery with that series internal resistance. Okay, I wanted to talk about current sources today, but we are going to be running out of time in a minute, so I'm just going to start drawing this, and then we will talk about it more next time. The difference between a voltage source and a current source, as you can probably guess, is that a current source, which we represent with this circle with an arrow in it, has an IV diagram that looks like this, where it can provide a constant current no matter what the voltage is. So this is a little less intuitive, and you don't encounter it as often because this is not how batteries work. But there are things like LED drivers, for example, that if you want to have an LED at a certain brightness, you need a certain current through it, so it's more important to control the current than the voltage. So you won't encounter these as often. Real quick, I got 1 minute left. I forgot to jot down an equation for the voltage source. You can then apply Ohm's law if you short circuit this. Yes, so if you do short circuit the practical battery, you no longer get infinite current. You now have Vs equals I Rs. So the maximum current you can get from the battery is Vs divided by that internal resistance, which for AA batteries is usually on the scale of a couple hundred milliohms. Again, talking about kind of resistance values, and you will see that in homework 2 too. Okay, we're out of time. I don't want to run over. We will pick up with current sources next time. Thank you.